Okay, welcome everybody. Thanks for coming along to an evening presentation of Oracle SQL Tuning Expert Understanding Indexes. I can see how excited everyone is about Oracle indexes, as evidenced by the crowd. I've got a big group here of DWS consultants and NAB staff. It's fantastic to see. A couple of administrative things. First, for those of you that don't know me, my name is Ross Leishman. I've been working with Oracle for more years than I care to remember. Primarily with SQL tuning and data warehousing and things like that. All of the things I'll be presenting tonight are my own learnings of about Oracle and about indexes. The venue we're here tonight at is the Bowl at NAB, so thank you very much to NAB for supplying the venue. It's fantastic to be able to fit everyone in and present to everyone and have room to set up the video and things like that. While I'm doing acknowledgements, I'd like to acknowledge Murray Armand and perhaps if we could just have a little round of applause for Murray who puts together these videos. Puts together these videos at his own expense of time and sometimes he has to justify extra expense for buying more disk space at home to do them. The video will be available on YouTube probably in a couple of weeks' time, and I'll be able to send out a link to you for it. The room here, we've got a kitchen out the back. If you're thirsty, you can get a glass of water or a cup of tea out there. The bathrooms are out past the security guard. Security guard can direct you from there if you like, if you don't know where they are. Anything else? Oh, questions. I'll take questions as we go. It is a large group here, so if you don't feel I answer your question on the first go, I'll give you one redirect to ask me to clarify. If that doesn't work, stay behind afterwards, and we can sort it out together without wasting the time of 82 other people. Administration, thank yous. Yeah, I think we're ready to go. All right. So, when I started putting this together, I thought about learning, and I thought about my learning process for Oracle and for indexes, and I decided that I learned about Oracle and indexes in a very different way to how I learned about other things. Like I recall, and it might be the same for you. I recall my first experience getting a brand new mobile phone way back in the 1990s. The day I got that thing, I read the manual. It was a paper manual back then, but read the whole thing cover to cover, found all the features in it, and looked up all the crazy gadgets that you could add onto it. I knew everything about it. I could go into work the next day and show everyone my new mobile phone. It was fantastic. The learning curve was incredible. I knew everything about that thing within a day of having it. Oracle, on the other hand, and indexes, I think I probably spent 5 years working on Oracle, and in that first 5 years, I don't think I knew anything about indexes. I didn't know how they were stored on disk. I didn't know how they were used. I didn't know when one would be used. I didn't know when one wouldn't be used. It was a mystery. It's not because there wasn't information available. It was all there in the manuals. I just didn't read it like I did with my mobile phone. So it's and you can see the magic quadrant I've prepared there. Is anyone familiar with Gartner? Gartner's magic quadrants? Yeah. Okay. So new technology and Oracle indexes are in very different quadrants of of my magic quadrant because one, very easy to learn. You know, the rate of learning is very high. Joy of learning is very high. Indexes, not so much.
Some of us would have to move one of those way over the list.
Which one, Murray? Okay. So I started work with Oracle in about 1990, I reckon. And by about 1994, I reckon I still knew nothing about indexes. My tuning methodology, as depicted on the screen here, might be the same as yours in your formative years. See what you think, or it might be. Don't admit this, but it might be the same as your tuning methodology now. So if something's going slow, try creating an index. And if that fixes it, you're done. If it doesn't fix it, Try creating another one. Does this sound familiar at least? Don't have to admit that it's familiar to you yourself, your own tuning methodology, but have you seen others employ this methodology? Yeah? Yeah, a few of you. I'm not ashamed to say this was my methodology in 1994, because I really didn't know what I was doing. My methodology today is different. Okay, and this is the abbreviated methodology. Now, I look at a SQL or I look at a problem, and I decide whether I need an index. And if I do, I create it. If I don't, I'm done. And there is a small footnote there. May require some understanding of how indexes work. And that's where this presentation comes in. Okay, who's heard of B trees? Right, yeah. Indexes are stored in B tree structures, aren't they? B tree data structures. Right, at least they are in Oracle. Do we know what a B tree is? Who reckons they do know what a B tree is? I'm not going to ask you. I'm not going to ask you. Yeah, some of you reckon. Some of you reckon you know what a B tree is. Okay, and I'm not saying you don't. I'm not saying you don't. You probably do. Okay. So the first thing I'm going to do is try to explain in easy to understand terms what a B tree is. But before I can do that, I need to backpedal a little bit. I need to explain to you what a database block is in Oracle. So let's have a look at this diagram here. The outer box there is a database file. No mystery there. Okay, a database file is just it's a file on the operating system where the database stores its data. Okay, easy. It's a piece of disk. Within that piece of disk, that's broken up into operating system blocks. Okay, so we understand that disks are broken up into blocks. Yeah, and a block might be half a K or something like that. You're familiar with that concept? Yeah. Okay. So disks are made up of blocks. In the bottom right-hand corner there, we see operating system blocks. See that this file is broken up into a number of operating system blocks. Now, Oracle's a database, not an operating system or not a disk system. Okay, it defines a block slightly differently. It doesn't define its database block as being part of an operating system block. It's one or more entire operating system blocks. So with Oracle, you might find that, say your operating system is Unix. Most Unixes, last time I checked, the operating system blocks were half a K. Does that sound familiar to anyone? Confirm or deny? Yeah, take that as confirmed. Okay. So your Oracle database block, well, it's configured at the time you install the database. That could be probably not going to be half a K. Could be 2K, 4K, 8K is the default. If you just click OK on everything when you install, you'll get 8K blocks. So you'll get 16 operating system blocks in one database block. Right. In this 16K block, most of the pieces of data that we read, most of the rows that we read, are not 16K. Okay, they're much smaller than that. It might be 100K. Okay, sorry, 100 bytes rather, not 100K. Gee, might be 100 bytes. So lots of rows are going to fit into a single database block, as depicted there in that tiny red sliver. That's one row in a database block. Now, in a database, we often deal in one row at a time. We're interested in retrieving and manipulating and perhaps displaying a single row. But we can't read a single row from the database. We need to read a single database block from the database. And that database block may contain 100 rows, might contain 500 rows. Okay, so if you think about the I/O that you're performing, I'm reading one row. You're not. You're reading one block. Okay, and you may have a terrible amount of wastage there. You may be reading a lot of rows that you're not using, and this is one of the most important concepts in SQL tuning is eliminating or minimising this wastage, the rows that you read from a block that you don't actually want. So ideally, if you're reading a block, it would be great if you need lots of rows. Wouldn't it be great if those lots of rows were actually on that block that you read? Then you wouldn't have to read multiple blocks. Okay, just read one block and you get all the rows you want. That would be wonderful. Okay, so database files made up of operating system blocks. Oracle database blocks are one or more operating system blocks. A database block contains lots of rows, and that's our minimum unit of I/O. We read and write to the database in units of blocks, not units of rows. When we write a single row to the database, we're actually writing an entire block. All right, I said I was going to talk about B trees. What does this look like? Is this a B tree? What's it representing? Anyone familiar with those names? Prime Ministers, thank you. Australian Prime Ministers even. Who did data structures at university? Yeah, I did. Who can name this data structure? Binary tree. Thank you. Any specific type of binary tree? Ooh, someone said the word balanced. Who said that? Okay. Is it balanced? Let's have a look at the far right-hand side. We've got Watson with Scullin and Whitlam as subordinates over on the right-hand side. It's missing a level over there. Whitlam's at level 4, whereas if we go a little bit to the left, Menzies and Reed and all of the other leaves there are at level 5, so it's not balanced. It is a binary tree. It is what I call a binary search tree, because apart from it's a binary tree because every branch node has only 2 children. Okay, that's the binary. Right? So up to but not exceeding 2 children. What makes it a search tree is that it is ordered alphabetically. Anyone remember from their data structures lectures at uni, in order search? In order searches? Just me. Okay. All right. In order search, if we go underneath this tree with an arrow pointing up, so we start with Abbott, Barton, Bruce, Chifley, Curtin, Deacon, Fadden. Okay, we're going that up pointing arrow. The nodes that we pass in the tree are we're passing them in alphabetical order. That makes it a binary search tree. So if we wanted to search for a particular row in there, like Keating, for instance, we'd start at the very root, Hughes, and we'd say, well, Keating, that's after Hughes, so we'll go right. And then Rudd, well, Keating, that's before Rudd, so we'll go left. Okay, and we can find our way down to Keating that way. Binary search tree. Wasted a lot of time on binary search trees because binary search trees have nothing to do with B trees. But when I first heard the term B tree, that's what I thought it was. I thought it was a binary tree or even a binary search tree because indexes are about searching for stuff, aren't they? Am I the only one here that thought that binary trees, binary search trees, were how B trees were implemented in databases? Just me and Andrew, right? and a couple of others. Yeah, it makes sense because I wasn't taught B trees at uni. I was taught binary search trees, never actually implemented one, never seen one in the wild. Okay, so that was a really good use of a semester. All right, so it's not. This is not a B tree. It is a binary search tree. It is not balanced. Okay, the B in B tree is sometimes thought to mean balanced. Certainly, B trees are balanced. Technically speaking, it doesn't. The B is not for balance. The B is not really for anything except possibly the initial of the guy who invented them. But it's a common thought that B trees are balanced trees. So this is what B trees aren't. What are they? Is this screenshot familiar to anyone? Most people here work with Oracle, don't you? Use the manuals at all? Online manuals? No, that's why you're here. Okay. All right, fair enough. If you did use the online manuals, one of those manuals is a wonderful thing. It's the master index. And coincidentally, the master index is structured almost exactly like a B tree. So it's a really good way to describe them. When I'm using the online Oracle manuals and I go into the master index, I'm presented with that top section there of the A to Z and the symbols and numerals. From there, in this particular screenshot, I've chosen P. Okay, and within P, I've got the choices PA, PC, PD, etc. And I've chosen PA, presumably, if we have a look at those index entries down there, they all begin with PA. So then you click on PA, and it shows you all the index entries beginning with PA. Okay, so we've worked our, you can see we've worked our way down a hierarchy to find the entries that we're interested in. Okay, we're still in the index, right? Because if we have a look at that top one, package body, if we click on that, that'll actually go through to a manual. In fact, the Application Express SQL Workshop and Utilities Guide. Okay, and we can think of the manual that we go to. That's the table. Okay, this is the index. Wherever the index takes us in the end, that's the table. All right. So the structure of this, what we're looking at, this very top layer is the root block. Every index has a root block. There's only one of them, and it's one database block, exactly one database block. Right? And that will have as many entries in it as it needs. Okay, this one, because we're humans and we think in terms of alphabet, that's got entries for A to Z and then symbols and numerals. That makes sense. In a database block, there's no guarantee that all the things that make sense to us are going to fit into a single root block. So it'll take the entire range of things that we want to index and break them down into enough chunks so that the header of each chunk will fit into a single block. Right? Below the root block, we have branch blocks. Right? So for any root block covers a range of index entries. That range of index entries will then be broken down again, and this can repeat for a number of branch blocks into 2 or 3 or 4 levels of depth, depending on how many index entries we have to put in our index. In this particular index, it only goes down one root block, one branch block, and then we get to our index entries. And our index entries are the things that take us to the table, or in this case, the manual. Right? So branch block is just like the root block, it just divides things up into ranges. Okay? And then below the branch block, we've got a leaf block. Okay, leaf blocks, the only thing special about leaf blocks is they don't have anything below them. Right? They just the entries in a leaf block take us off to the table, whereas the entries in a branch block or a root block just take us somewhere else in the index. That's the only difference. Right, so this is a really good analogy of a B tree index. It's got root blocks, branch blocks, leaf blocks, and the entries in the leaf blocks take us off to the table. All right, let's have a look at a particular B tree index. Okay, so the structure on the left is the B tree index. The vertical structure on the right is the table that the index refers to. Okay, so this is an index of the prime ministers that I went through before, and we can see that that all of those how many prime ministers have we had? Anyone? I don't know. About 34 or so. Sound about right? Okay. Yeah. Let's say 34. Ross. Yeah, good. Okay. Those 34 prime ministers are broken down into. I'm saying that my index blocks here can take 4 entries. Okay. In a real Oracle database, it'll be much more than 4. Okay, but it's good for the purposes of illustration here. Right, 4 entries. And the 4 entries I've got in my root block are Curtin, Fisher, Rudd, and Whitlam. Okay, and so what we're saying is Curtin, right? Everything that's alphabetically before Curtin and including Curtin is going to be wherever that block is pointing. Anything past Curtin up to and including Fisher will be subordinate to wherever the Fisher address is pointing. Okay, we can see that the Rudd address, which is everything from Fisher to not including Fisher, up to and including Rudd, goes down to the next block, right? And this is another branch block. It's not a leaf block yet. Right, the branch block, we've got Gorton, Hughes, McEwen, and Rudd. Okay, and then that goes down to 4 different leaf blocks. Okay, by the time we get to the leaf block, those entries in the leaf block are pointing to rows in the table. Okay, notice how those blue lines that go off to the table, they're not all parallel. They're not. So we've got Menzies, Page anyway. Yeah, sound right? Maybe Page. Yeah, Reed and Rudd. Okay, they're not rows 13, 14, 15 and 16, okay, they're scattered all over the table. If the table was nice and ordered, we wouldn't need indexes. Okay, so the table is not ordered at all. The index is ordered, and the consecutive index entries could point anywhere in the table. All right. So how does this work? The B tree, or how is it different from the binary search tree that we looked at before? Each entry in the B tree, it's an entry. The entry is a block, not a the node in the B tree is a block. It's not a name or an entry in the table. So in our binary search tree, each node was a name. So read and rud, they were each nodes in the tree. Whereas we've got blocks in our tree here, and each block contains multiple entries. Right, each block contains multiple values, one child per block. Leaf entry. Once you get down to the bottom, leaf entries point to the table. Okay. All right, the depth of an index. So my index here, because I'm only allowing four entries per block in my index. So at the third level, at that leaf level of my index, I can have 4 to the power of 3 possible rows there. So I could have, at level 3, I could have a maximum of 64 rows in my table. Right? If we think about a more practical example in a database, if we used 8K blocks, right, we had an index on surnames or a date or an integer that average out about 8 bytes or thereabouts. Each index block would hold perhaps as many as 400 index entries. At level 3, so this is a 3-level index we've got here, we could fit 64 million rows there. At level 4, we could fit 25 billion rows. So we can see that indexes in Oracle, when you're in 8K blocks, don't actually need to be that deep. Okay? If you're traversing an index from root, branch, leaf, off to the table, right, you're probably not going to have to read more than 4 or 5 blocks to look up a single entry in the table, even if that table has millions or even billions of rows. So when someone says, "Oh, this system, it's all very well to say it works with a million rows in the table. What's it going to be like when we put 100 million in there?" About the same. Okay, because indexes don't get much deeper. Once they get to about level 3 or 4, not getting much deeper.
Where is the 65th Prime Minister going to go?
In that, well, interesting that you ask where the 65th Prime Minister is going to go, because we're going to get to that in just a minute. Okay, so this is something you can try at home. If you've got a particularly big table in your database, you could run this SQL. We're familiar with the data dictionary in Oracle, the user indexes view in the data dictionary. There's a nice column in user indexes called B level. Okay, B level tells us the branch level of an index, not counting the leaves, which I thought was strange. So I add 1 to it, and that gives me the full depth of the index. So you could look up the user indexes table, and it'll tell you the B level. Add 1. That's how deep your index is. Okay, I'd be surprised if anyone found one that's more than about 4 levels deep. Okay. Righto, moving on. Unbalanced B trees. Okay, since none of you remember binary search trees from uni, I'm the only one. Okay, only I would remember that one of the problems with binary search trees is that it is possible to get them very much unbalanced. If you insert rows into your binary search tree in reverse alphabetical order, you end up with a binary search stump instead of a tree. Is that ringing any bells to anyone's? Yeah. Okay. As this is possibly a stump here. So can a B tree is exposed to the same problem? If we inserted rows into this table has an index on surname, obviously. If we inserted rows into this table in reverse alphabetical order, would we get the same thing? If we went Whitlam, Watson, Scullen, Rudd, Reed, I'm sorry I've abbreviated all these and I've got to memorise the names, would we end up with this reverse ordered stump? We wouldn't. In a binary search tree, you would, but B trees are always balanced. Okay, this tree is not balanced because the other well, actually it is kind of balanced. It's each index entry only has one node in it, and it's at level 5. If that first if we went Whitlam, Watson, Scullin, Reed, Rudd, Reed, and then we inserted Zaharakis, that would go into the root block, okay, or it might go. So then Zaharakis would be at that would be at level 1, and we'd have other things at level 5. Okay, and it's unbalanced. Not everything is at the not every leaf is at the same level. So B tree is always balanced, and this is how they balance, and this is how you create new levels in your B tree. All right, how B tree is balanced, part 1. Right, so say we've got a block. Okay, a block in our example contains as many as 4 entries, but we've only got 3 in there. Right, we've got Barton, Deacon, and Watson in our block, and we've got 1 blank space at the end. Right, we want to insert Reed. Okay, Reed goes in the middle of Deacon and Watson. Yeah, right, but our blank space is on the end. That's no problem. Okay, all we want is four entries in our index. We can rewrite the entire block. Remember, in Oracle, our minimum unit of reading and writing is one block. It's not like it's going to cost us anything more. When we want to write 1 row to our index, we've still got to write the entire block. If we want to rearrange that block, that's fine. Okay, it doesn't cost us anything extra. So we read that block in, we go, Reed needs to go into this block. It fits in the block, so what I'm going to do is I'm going to reorder the rows in there, Barton, Deacon, make a space, put Reed in there, Watson, okay, and write the block back. Right, so when we've got a block with free space in it, and the row that we want to insert, alphabetically or numerically, if it's a numeric index, belongs in that block, we just rewrite the block with the extra row in it. Part 1. Part 2, our block is full, all right, and we've got Barton, Deacon, Reed, Watson, and we want to insert Fisher. Fisher goes between Deacon and Reed, okay, but there's no free space. Okay, it's not going to fit in this block. So at this point, what we do is we split the block. Okay, this block has 4 entries in it, so we're going to take the first 2, Barton and Deacon, the second 2, Reed and Watson. We're going to write them to separate blocks. Right? And the block that we're looking at, it has an address, and that address is pointed to by its parent, by its branch block. Right, what we're going to do is, because we're creating a brand new block, we're going to put the address of this brand new block in the parent. Okay, presumably there's space in the parent. If there's not, okay, we're going to do the same trick as what we're doing here. Okay, so we've split the block into 2. We've inserted Fisher where it logically belongs in the first block there. Barton, Deacon, Fisher in that block. Now we've got a nice, some nice free space over in the Reed and Watson block in case we get some more Prime Ministers that belong over there. We've got 1 free space in our left-hand one, right? And what we've found is, oh, hang on, we're actually at the root here. There's no parent for me to put the address. I've got 2 blocks now. I've got to put the addresses of those 2 blocks in a parent. So what I'm going to do is I'm going to go up. I'm going to create a new level in the index, a new root level in the index. I'm going to put those addresses in there. So when we run out of space at the leaf level, we don't add below that leaf, because that would unbalance our index. Okay, if we had a beautifully balanced index with hundreds of leaf blocks, all of them full, and then we go to insert 1 new row in this 1 leaf, and then we split it and extend down that one branch of the index, then it's going to be at level 5 and everything else will be at level 4. It's unbalanced. Okay, what we do is we split it, leave it at level 4, cascade back up to level 3. Oh crap, no room there. Split that, cascade up to level 2. No room there. Split it, cascade up to level 1, which is the root. No room there. So we split that, create a new root, okay, and 2 addresses in it pointing to the old block and the block that we split. Because we add the new level at the root, we're always balanced. Okay, it was balanced before we started. It's the root that's split. Everything subordinate to the root encompasses the entire tree. So if we go from, I'll get to you in a minute, Andrew. If we go from level 4, we split the root, add a new root in. Every leaf is now at level 5. Andrew.
If you continually add record with one at either end of the spectrum or any given point in the spectrum, wouldn't you end up with a technically balanced tree where a vast majority of the entries are on one side?
What you would find, say you had an index that was sort of nice and even, okay, like this, and we had a spate of 500 prime ministers that were W and and beyond. That's the sort of scenario that you're talking about. What you'd find is after you've filled up the leaf level, and you get to the first point where everything's full at that level, you need to split the root. The root is going to have, say, Barton to Watson, or sorry, the root will have 2 children, Barton to Watson, and then another child being Watson to beyond, okay, and then so up to Watson, the left-hand side. That will be as full as it is, and the right-hand side that'll be as full as it is. So you'll find the root block won't be nice and even, won't be like A to K, L to Z, right? It'll reflect the distribution of your data. Does that answer your question? Cool. Righto. So that's yep.
Is that when the index split happened? If you got multiple sections divided by index entry to index, when the split happened, then whole index is locked out and the other section has to wait? Okay,
locking of the index is it's a little bit outside the scope of this presentation. Do you by any chance work with SQL Server?
No.
No? Okay. With Oracle? Okay. Oracle deals with locking, especially in indexes, fairly elegantly. Actually, it won't lock the entire index down. The intent is that it just locks the rows in the index that you're working with, and it does it in quite a clever fashion that is way beyond the scope of what I'm talking about here. But if you get yourself in a situation where an entire index is locked and congested, then you're probably either dealing with an Oracle bug or a bitmap index. You're not thinking about bitmap indexes? B-tree index? Yeah. I certainly haven't encountered it. I understand how locking works in indexes. I can't see how it would happen unless you had an inordinate number of concurrent sessions working at once.
Like, because when the split happened, then you have to split the branch and you split all the way up.
Yeah.
So you got 2 of them instead of the same time. You don't.
Okay, we'll have to take that one offline. If you want to talk to me about it later, then feel free.
Just confirm, Ross, that if you happen to find the one that you're after at the root level or some intermediate level, you still have to go all the way down.
Okay, right. So I didn't make that clear. That's it's a good question though. At the root and branch blocks do not contain index entries. They just contain addresses to more blocks in the index. So. And my oversimplified example here doesn't make that perfectly clear. The index entry itself. So this is an index on surname, for instance. Okay, an index entry has 2 things. It's the thing that you're searching on, the surname. Okay, and it has a payload being the address of the row in the table where that entry can be found. Okay, so for Watson, for instance, there is a row in the table that has a surname of Watson. That row in the table has a row ID. Okay, and that row ID is found in only one place in the index, and that's in the leaf level. What's found in the root and the branches is pointers to more index levels. Okay, and only once you get down to that leaf level will you find the table address. Okay, the address in the table where you can go and find Watson. Does that answer your question?
Yep. So
great.
If you've got a 4 level, always there's 4 reads.
Yes, yep, so yeah, no shortcuts. Okay, Right, so, so like I said before, extra levels in the index are added at the root, not at the leaf, and that way they're always balanced. Okay, how do indexes improve performance? This is the thing that it took me about 5 years to work out. So when we think of indexes, I usually think of only one purpose, and that is, you know, finding a particular row or a small number of rows, avoiding a full table scan. I've got a table with 10 million rows. I don't want to read all 10 million. I want a mechanism to go to just the row that I'm interested in, or just the few rows I'm interested in. And that's the first use of indexes, avoiding a full table scan. Indexes are actually good for two other things as well: avoiding a sort and avoiding accessing a table altogether. So I'll cover both of those. But first, avoiding a full table scan. Okay, so so here's our index again, or a depiction of our index, and here's a SQL that we might run against that. Select star from Prime Ministers, where surname between Gillard and Holt. Who knew that you could use indexes to evaluate a between condition? Yeah, 2 of you. Okay, 3. Okay, good. So it's not just equals conditions. There's lots of other conditions that you can use an index for. If you think about it, it's actually fairly logical. If you thought about an index in a book, could I use, if I had a book that was indexed on surname of Prime Ministers, could I use that index to find all of the Prime Ministers between Gillard and Holt? Yeah, sure. You go to G, find Gillard, and then start reading down the index until when you get to Holt, you stop reading. Makes sense. Okay, so if you could do it with an index in a book, then Oracle can do it with an index in a database. So we start at the root block. You like my nice wiggly line there? That was me with a mouse trying to do a smooth line and failing. So we look at the root block. We want to start at Gillard. Okay, so Gillard in this, looking at this root block, Gillard is between Fisher and Rudd. Okay, so the path that we want to follow, we know that Rudd is the end of that third address in the root block. So we know it's after Fisher. So we're not interested in the Fisher block. That's everything before Fisher. We know Gillard's not before Fisher. Okay, so we want to go down the third path there. So we follow that third, looking for Gillard. We follow that third path down to the first branch level, and we see Gorton, Hughes, McEwen, and Rudd. We go, well, Gillard is before Gorton. Yeah, so we want to take the first branch there out of that branch block. So we go down, take the first branch. We've got anyone, F-O-R, Ford. Yeah, there's a Ford. Okay, good, thank you. Fraser, Gillard, and Gorton. Okay, and remember, our minimum unit of I/O in Oracle is a single block. So I've read that entire block. Not interested in the Ford and Fraser. Okay, we've read the entire block. We look where Gillard is in that block. Okay, and we're ignoring Ford and Fraser. Gillard, that's what we're looking for. Beauty. So we read Gillard and we output that, send that to the next step in the execution plan. In our case, we're just going to look up the table and then pump it out to the screen. Okay, so see Gillard, and then we move right. Gorton, fantastic. The other thing, apart from these addresses that link hierarchies in the index, we've got another set of addresses as well. Addresses that link leaf level blocks in the database. So once I get to Gorton, I don't have to trace back up the tree and down again to get to the next logical leaf. I can just, there's another address sitting in that block that tells me the next logical leaf block. Right, so I don't have to go down, up, down, all the way back up the root, down again. Okay, once I get to the leaf, I can just progress on leaf block to leaf block. So at the end of that block, nice address to the next one, which is Howard, Hawke, Holt, and Hughes. Okay, and I'm still, I got up to Holt, and I halted Holt. All right. So when I see Hughes, I know I'm done, and I don't need to progress any further. So I've started my range scan, progressed to the next block, found Holt, or if Holt wasn't there, if I got alphabetically past it, then I'd stop looking, and that's the end of my range scan. So that's how a non-unique index scan works, right? Avoiding a full table scan. So avoiding a sort. Imagine if we had this SQL here: select star from Prime Ministers, where the party's ALP ordered by surname. Okay, not equal to conditions, like party not equal to ALP, they're not really, they're not something that you can index. You know, equals conditions between, yeah, they're good. Not equal, not so much. Okay, but look at this, order by surname. Oh, hang on, we've got an index on surname. Indexes are ordered. Okay, the leaf blocks, the logical order of leaf blocks has all of our prime ministers nicely sorted. We're running a SQL where we want to order the results. We've got no convenient index to find the rows. Okay, it's not like, you know, party equals ALP where we could, you know, maybe use an index on party to find the rows. So we're up for a full table scan anyway, right? Full table scan, and then I've got to sort it. Okay, or what if I use the index instead that's already sorted and just read the rows off there in sorted order and avoid the sort? Yeah, Oracle can do that. So in this particular case, it's going to do a full index scan. Who's heard of full index scans and fast full index scans? Yeah, this is not a fast full index scan. Okay, it's slow. So we start at the first logical block in the index, and we find that by we actually start at the root. We go curtain. We go all the way down the left-hand paths until we found the first logical block in the index, and then using those linkages between the leaf blocks, we're just going to read the entire index, okay, from left to right, every single row. And with each one, we're going to look up the table. Go, ah, no, he's not ALP. So I'll keep that row. Or he is ALP. I'm going to discard that row. So you can see there, we start at the left-hand side, read a block, go forward. No, he's not. Sorry, he is ALP. So get rid of him. Fraser, no, he's not ALP, so therefore we want that row, project that row. Okay, Gillard, she is ALP, chuck it out. Gorton, etc. And reading on to, to each block, and the results, Fraser, Gorton, Howard, Holt, Hughes, they're all in alphabetical order. And we've done it without having to do a sort in the database. Right? So indexes can be useful for that. Avoiding a sort, you can't avoid all sorts, okay? When we think about sorts, yeah, order by, yeah, you're going to get a sort with an order by. You might know that group bys will often use a sort. In more modern versions of Oracle, there's other methods of doing a group by, hash group bys, so you don't always have to use a sort for that. Distinct, there's hash distinct now as well with modern versions, but you used to always have to use a sort for that. With those three, you can engineer it so that it will use an index to avoid a sort. Things like union, minus and intersect, analytic functions, sort, merge, joins, uncorrelated inquiries. Some of those things will also cause sorts in the database. I've never yet found a way to use indexes to avoid any of those sorts. All right, avoid accessing a table altogether. Have a look at this SQL. Select party from prime ministers where surname equals Holt. We've got an index on surname. Fantastic. There's probably not many entries in this table that have Holt in them. So we're going to use the index on surname. But what we want from this SQL, we want to select party. So party's over in the table. Right, so once I've found Holt in the index, I'm going to have to look up the table, right, to get party. What if I dropped that index, recreated it? So create index, Prime Minister's surname IX on Prime Minister's, and I added another column to the index on surname and party. Right, so now, when I'm looking in the index, I can scan on just surname. I don't need to scan on surname and party. I can scan on any leading subset of the index. So I'm reading this index by surname. I've found Holt in there. Fantastic. All right, what do I want? What does this SQL want? Well, it just wants party where surname equals Holt. Hang on, I've got party sitting in the index. Do I need to look up the table? No. Right? I've got everything I want sitting in the index. So if all the columns that you want are in the index already, then you don't need to look up the table. Right? And depending on the criticality of the SQL that you're working with, it might be worthwhile adding an extra 1 or 2 columns to your index to avoid table lookups. Okay? It would have to be really critical SQLs for you to decide to do that, but it is a tuning technique. All right, comparison operators. All right, I said before that we could use between and we can use equals. So here's pretty much a full list. We can use equality clauses, equals and in lists, where in A, B, C, D. Okay, that's an equality condition. We can use range clauses, greater than, less than, greater than, equal, less than, or equal, between, and like. Okay, like, it's like a range clause. If you have like ABC percent, that's sort of like, you know, between ABC and ABC Z Z Z Z Z Z Z. If you're just talking alphabetics, right? So that's it's very much like you could sort of rewrite a like as a between, as long as the percent, the wildcard, wasn't at the beginning. Okay, if you do like, you know, percent ABC, you can't do a range for that. Okay, that's not going to work. So likes with a leading non-wildcard, okay, they can use indexes as well. Any not predicate, if you've got any negativity in your predicate, it's not going to use an index. Not going to use a B-tree index. Okay, not ins, not equal to, not greater than or equal to, not like, not between, not going to use B-tree index. Null predicates won't use a B-tree index. That's is null or is not null, anything like that. It's not going to scan on the index. Okay, because yeah, can't scan for something that's not there. That's B-tree indexes. Oracle supports another type of indexes, being bitmap indexes. I'm not going into them here, but the rules change for bitmap indexes. But if you've got one of these nots or null predicates, don't just go for creating a bitmap index, please. All right, what expressions can use indexes? Okay, so the things that we've looked at so far, we've indexed the surname, and then we've done queries on surname. What if we did a query on substring of surname, put the surname in a function? That's not going to use the index. What you find is that some functions or some expressions can be re-expressed, right, by changing around the syntax in a way that that can use an index. If you have a look at these, we're looking for surnames where the first four characters are M-E-N-Z. Menzies, really, aren't we? Another way of expressing that is where surname is like M-E-N-Z%. That will use an index, okay, but the substring won't. And sometimes we find that, especially with substrings. That's there's a good way to do it, use an index, and a bad way that doesn't. It is possible to create what's called function-based indexes. Okay, instead of creating an index on surname, we can create an index on substring surname, comma 1, comma 4. Right? It's a very, very specific type of index. If we did another SQL on substring of surname, comma 1, comma 5, it's not going to use the index on comma 1, comma 4. Okay, it only works when your SQL exactly matches it. Right, but it's a technique that you can use, function-based indexes. Just be very careful with function-based indexes. It's very easy to allow them to proliferate. If you get lazy, write your SQL first, tune it later by adding function-based indexes, you might find you have a lot of indexes. All right, logical operators. If we've got an index with two columns, a concatenated index, so we've got Prime Minister's table, index on party, and year elected. How can we scan on both of those columns at once? Only with an AND clause, where party equals ALP and year elected is greater than or equal to 1980. That AND condition, so one on the party, one on the second column of the index, year elected, right? If they're combined with an AND, then you can scan on both columns at once. You don't have to have that second one. You can scan on just party, if you like, on a concatenated index. If you had where party equals ALP or year elected is greater than or equal to 1980, it's not going to use certainly not going to use it in the sense of being a concatenated index. At the very best, what it might do is go, well, party equals ALP or year elected is greater than or equal to 1980. Okay, I'll do two scans, right? I'll do one just on party because I've got an index on that. If I had another index where the first column was year elected, I might do a second scan on that one. That's possible. It's not going to use a concatenated index. It's not going to use both columns of a concatenated index for an OR condition. Not conditions, forget about it. Okay, not as anywhere where you see a not, that's death to indexes.
Ross?
Yes.
So just to confirm, if I was to comment out that AND statement,
the last one, the last line, line 4.
Yep. That index wouldn't get used.
No, it could get used. Okay, if you're using a leading subset of the index, then you can scan on a leading subset. So this index is on party and year elected, which means we can scan on party and year elected combined, or just party on its own, or party and a range of year elected, which is what we've done here, or just a range of party. Yeah?
But if I've done it with where my where clause is year elected greater than 90.
Oh, if you struck out line 3, okay, that's not going to use the index.
Okay,
If
so
you're
it has to be the first one.
It does. It has to be a leading subset, and if anyone's going to yell skip scan at me, out of scope of this of this presentation. There is an exception, but I don't want anyone designing applications that use skip scans. Righto, group exercise. Time for some fun. We've only got 5 people in that second row. If someone, say Carrie for instance, wants to move into the row in front, I'm going to use the first 2 rows of this side of the audience. You don't have to do anything except I'm going to. I've got some cards in my case. All you have to do is hold the card and give it to the volunteer when they ask for it. Okay. Calling for a volunteer. If no one sticks up their hand, I'm going to choose one at random. I can see Geordie looking in through Jordan, Peggy, just stand beside the whiteboard here. Your job will begin in just a moment. Okay, for the group exercise, what we're going to do is simulate an index. I've got a couple of SQL statements here. Have a look at those. Select surname party from Prime Ministers where surname equals Menzies. We're going to use an index on surname. And select surname from Prime Ministers where party equals AOP. I've got another index on party. Righto, I'm going to hand out to first and second row of the audience here. These are blocks in a table. So you guys, row 1 and row 2 on this side of the audience, you're the table, okay? And each one of you is a block in the table, okay? So channel the block, okay? Channel the database block, all right? And each one of you will have a card. Jordan has the special role of he is the buffer cache. Anyone know what buffer cache is?
Never been called a buffer cache.
Never been called a buffer cache before. It's a very responsible role. Okay, I've got index blocks here as well, the index cards, but the index cards will be in the buffer cache, or in the hands of the buffer cache in this example. Here's an example of the index block. If we have a look at the very first entry in the index block, this is an index on surname. So I've got surname Abbott. Abbott is going to be found on card 12, or block 12 in the database, row 1. So first row, 12th card of the database. That's how indexes work. I'm not going to attempt to replicate in this example the B-tree structure of the index. I've already explained that. I assume you get it. Right, so I'm going to hand out the table blocks here. I see I've still got only 5 people in row 2. Can't carry. All right, I've got block 1, 2, 3, 4, 5, and 6. And Karen, could you pass those down, please? Keep 7 for yourself. 7, 8, 9, 10, 11, and 12. Okay, buffer cache? Buffer cache. Clear yours. All right. So, I've handed out my table blocks. I've appointed another participant, the buffer cache. It says here I'm going to appoint a participant, the user background process. I'm going to be the user background process, okay? Most responsible role. The user background process. So, when you're running a job on Oracle, there's a process that's running on the CPU. That's the user background process. It's the thing that's doing all the work, okay? And as you can see here, I'm doing all the work. Okay, so we're going to simulate an index scan for the following SQL. Select surname, comma party from Prime Ministers where surname equals Menzies. Righto. So, what we want to do is come over here to near my buffer cache. Right. We're going to find Menzies in the index. So, buffer cache, could you...
Bang, look how quick I am.
No, look. Buffer cache. Does everyone know what the buffer cache is? Apart from... the buffer cache... The buffer cache. You're supposed to heckle me. The buffer cache is an area of memory in our database. Okay, as the user background process, all right, I want everything to be, I want to read stuff from memory. I don't want to be getting stuff from disk. Okay, so when I read a block, I'm going to leave it in memory. Okay, and then I can come back to it if I need it again. Right, and so buffer cache is that area of memory where database blocks are stored in case I need them again. If my buffer cache gets full, because you've only got two hands, right, you can't hold too much at once, right, things are going to get aged out of the buffer cache. If I need that block again, I'm going to have to go back to disk to get it. Right, but I'm the user background process. I'm the one doing all the work. Buffer cache is just showing me stuff. Buffer cache is not talking and stealing my limelight.
Buffer cache is in a minute.
I'm beginning to regret choosing a buffer cache with a louder voice than me. Okay, so the background process is going to read the index block from the buffer cache. So buffer cache, please hold up the index block, thank you, for the surname index. Right, so I'm going to find Menzies in that. Okay.
Do I show you?
No,
what does the buffer cache do?
The buffer cache is just showing. Okay, I'm going to learn. I'm going to find Menzies. There it is. It's in alphabetical order, so I'm going to go down the B tree. I'm going to find Menzies in there. There it is in the third column. And I can see Menzies actually had two terms as Prime Minister. He's on card 6, row 1, so whoever's holding card 6, you can see that, and card 7, row 3. Alright, so as the user background process, I've found that, and I know, because I've read the index, I'm going to need cards 6 and 7. Okay, buffer cache, do you have blocks 6 and 7?
Do I have blocks 6
Do you
and
have
7?
blocks 6
No,
and
I do
7?
not.
Where are we going to get them from?
I think I'm going to ask a table.
We're going to get them from the disk. Okay, so disk, the holder of card 6 in disk, could you please hold up your card? 6, oh there we go, so I'll carry 7 here. Okay, so Michael, thank you. Buffer cache, could you please go get card number 6 for me?
That's Oracle. I'll do that in SQL Server.
Okay, so now that I have card number 6 next to the buffer cache to hold the card, because I'm using background process, that block is now in memory where I can access it. Okay, so looking at card number 6, I'm looking for Menzies because that's my SQL select, blah, where surname equals Menzies. There it is, I found it. It's the first row. What am I doing? I'm selecting surname is party. So Menzies is the surname, UAP is the party. Anyone UAP?
United Australia.
Yeah, okay. Right, so I'm the user background process, so I'm going Menzies UAP. Okay, this is
For the Liberals.
right.
Yeah.
So I've found that. Now I also know, because I looked at the index, that there's more to come. Okay, I need block 7 buffer cache, please, from the table. Could you please get it? Do you have block 7?
I do not have block 7.
Could you please get it from the disk for me?
Is it Oracle?
Yes. Okay, no, buffer cache, hold the okay, looking at that, I see Menzies again in row number 3. Ooh, he's liberal at that time. Okay. Right, so I'm going to project onto my output Menzies lib. Okay, and now looking at the index, that's the end of. I've done my range scan from the top of Menzies to the bottom of Menzies. The next one after Menzies is page, so I'm at the end of my index scan, and I'm all done. How many block reads do I do? 2. Cool. Okay, cool. So I went back to disk twice. What's the most expensive bit of that operation, other than the buffer cache giving me trouble? What's the most expensive bit of the operation? Excuse me?
Going to disk.
Going to disk, yeah. Okay, I did it twice. Right, so Murray, could you please progress the next slide for me? Right, retrieved, I just did all that. Could you progress to the next one? Okay, full table scan. So now, same SQL, I'm going to do a full table scan. Could you please hand back block 6 and 7? I could do it with block 6 and 7 in buffer cache, but I'd be getting an unfair advantage then. So I'm going to reset. Okay, I'm going to reset to how I was. So surname party from Prime Ministers, where surname equals Menzies. Murray, could you please progress to the next slide? Righto. So this is a full table scan. Your indexes buffer cache are useless to me now. Okay, we're going to pretend those don't exist because we're going to do a full table scan. Right? Underline that. Right, so with a full table scan, I'm not reading the index. I'm going to start at block 1 of the table. Let's got block 1. Table. Great. So, Buffercache, slowly, not in Oracle record time, could you please go and get block 1 from the disk for me? Ah, stop! Because this is a full table scan, okay, Buffercache, by the way, this read that you're doing from the disk is a full table scan. After I get you to get block 1, I'm just going to keep on going.
I was going to say, we're going to do this.
So while you're about it, when you get block 1, even though I'm not asking for it yet, I've only asked you for block 1, could you please be a bit clever and get blocks 2 to 6 while you're about it? Okay. There's an initialization parameter in Oracle called db file multi-block read count. And when you do a full table scan of the database, whatever number is in there, say it's 64 or something, that's how many blocks will be read in a full table scan. When you go to get 1 block, you will get 64 blocks into the buffer cache. Okay, buffer cache, can I please see block number 1? Menzies, not there. Block 2? Menzies, no. 3? No. 4? No. 5? No. 6? Oh look, Menzies. Okay, number 1, Menzies UAP. So, Menzies UAP. Block number 7?
I don't have it.
Oh! Could you please go back to disk and get block number 7 for me?
Using my parameter.
Using your DB file multi-block read count of 6. Okay, I want you to 6 blocks. Just please hand them down. Please try and get them in order.
Make the next bit interesting.
Alright, bring back. Can I see 7 please? Buffercache. Beautiful Menzies lib. Okay. Menzies lib. Okay, fantastic. 8, no. 9, no. Yeah, 10, no. 11, no. 12, nothing, no Menzies there. Right, so I've done a full table scan, I've read all of those, and that's actually a good exercise. That's how fast stuff can be read from memory. Okay? Reading from memory and reading from disk, very, very different things. Reading from disk slow, reading from memory, very, very fast. Okay, how many times did I go back to disk? Twice. Can we progress the slide please? Maybe 2, yeah, 2 because I just did all that. Alright, so which one was faster?
The second one.
Same.
I went to disk twice.
You have to go to the index for this.
Oh, I had to go to the index first, but the index was already in the buffer cache. Oh! About the same. So the big things that we're measuring, the trips to and from disk, okay, about the same. How would it have been different with the index scan with the first one if I'm still looking for 2 rows Menzies, but what if there were 10,000 blocks in the table? How would that be different?
You would only have to go down 4 rows, or 4 levels or something?
Okay, sorry, you're absolutely right. The B tree itself might be a bit deeper. Well, let's say for the sake of argument, all the blocks in the B tree are in the buffer cache. But we often find that with index. Our buffer cache is probably going to be more index, less table. Okay, so the chance of when you want an index block, there's a much better chance of it being in the buffer cache than the table block being in the buffer cache. So you're absolutely right. With a 10,000 block table, our B tree will be deeper, and you could end up, especially if some of those blocks are not in the buffer cache, you could end up doing more reads. You're right. But mostly speaking, much the same. Yeah, if there's 2 rows from the table, you've got to go back to the table twice to get those 2 rows. The second example, table scan, how would that be different if there were 10,000 blocks in the table?
You have to do 1,667.
You'd have to do 1,667 returns to disk. Thank you very much, John. Great. The buffer cache be busy.
Question, can you set that max extent parameter to 10,000 in that instance and just go once?
Okay, good question. So DB file multi-block read count does have a maximum value, and it's dependent on the operating system as being the most number of blocks that your operating system and hardware can efficiently return from disk in a single visit. Okay, that's not going to be 10,000.
It's not going to be 10,000.
No. Right. Could you please hand those back? Try to get them in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 again. And Murray, could you please progress the slide? Okay. Exercise number 2. We're going to do an index scan of a different index. Bhavkash, could you please get your second index out? This one is on the party. And the SQL that we're going to simulate here is select surname from prime. This is where party equals ALP. Murray, could you go to the next slide, please? Righto. So we're going to find ALP in the index. Right, before when I was looking for Menzies, not so many. This time for ALP, lots of entries in there. And I can see I'm going to have to go to card 1, 2, 3, 4, 5, 6, 7 twice, 9, 10, and 11. Oh, gosh, so busy. Right.
SQL's never make him up.
So, Bhavkash, could you get me block number 1, please? Thank you. Looking for ALP. ALP, there is one there. Watson, ALP. So we're projecting surname, just surname, Watson. Okay, no others there for ALP. Could you get me block number 2, please, Bhavkash? Lovely, thank you. ALPs, there's no one there. It's Fisher. Okay, number 3, please, Bhavkash. Okay, seeing a pattern here. All right, Fisher again. Popular. Okay, number 4, please. Oh, Bhavkash, no, it happens in Oracle. All right, we've got Fisher and then Hughes going from ALP to Nations. Oh, okay, Fisher and 3 terms. It's popular. All right, Fisher and Hughes. Okay, do I need to keep going? Seeing a pattern here, one done. Okay, we've gone back 4 times already. You can see I'm going to have to go back like 10 or 11 times. Okay, and what we're doing is we're reading one block at a time. Could you please hang on that buffer cache?
That previous parameter you mentioned where the buffer cache will read
DB file multi-block read count.
Yep.
Yeah, only used for full scans. So full table scans and fast full index scans. What we're doing at the moment is an index range scan. Index range scans, a single block. When they go to the table, they're a single block. Okay, Murray, could you progress to the next slide, please? And again. All right, so now we're going to simulate a full table scan. Everyone's got their cards back. Next slide, please. Okay, so buffercation, I'm going to need block 1, but this time we're doing a full table scan. So DB file multi-block read count of 6, please. All right, buffercation has gone to disk once. Show them in order, please. So ALP, we've got Watson again. We've got number 2, second one. We've got Fisher. That's a surprise. Never guessed that. I'm going to guess there's another Fisher on the next block, please. Okay, yes, Fisher, thank you. All right, and on the next one, we've got Fisher again. Oh, it's upside down, my page. It's like this. Okay, we've got Fisher and Hughes. Okay, I don't need to keep going. All right, so first example, I went back to disk like 10, 11 times if I had to run it through to the end. Second example, I went 1 and I would have kept on going to 7, I would have gone back to disk a second time. Which one's going to be faster? The second one. Right. Murray, could you press the slide, please? Okay. I'm sorry, and again, I keep on, I should do these as I go. All right, so which method was faster? Second one. What would happen to the first example, the index scan, if there were 10,000 table blocks? Assuming similar distribution of ALP,
10,000.
for instance. Maybe not 10,000, but lots. Okay, lots of to and from the disk. What happened in the second example if there were 10,000 blocks in the table, in the full table scan example? Which is John? 1,600. Fantastic. Okay, so we can see that the first one, the index scan for these poorly selective index scans, they scale terribly. Okay? The second example, full table scan, they scale gracefully. Okay? Because of my DB file multi-block read count. That is it for the example. Thank you. Round of applause for George. Righto. So just one last exercise to finish out. This is not a participation exercise at the board. I don't need a buffer cache for this one. Just some examples. Call it out. Don't need to put up your hand. What would you index in these SQLs? So we're selecting customer name, customer address, last invoice date from customers, where customer number is 3456. It's exactly one row. So customer number is unique in this table. What's good index? Yell it out. Customer number, yes, beautiful. Okay, so if I had an index on customer number, I'd go straight to that row in the index, straight to the row in the table. From that row in the table, I'd read my customer name, customer address, last invoice date, and I'm all done. Okay, don't have to read the 100,000 rows in the table. So customer number, good index. Anyone disagree? No, fantastic. Similar sort of SQL here. Customer name, customer address, last invoice date from customers. This time where my last invoice date plus 365 is less than today. So I'm interested in customers that haven't been invoiced in the last 12 months. And that's, so most of my customers are active, so there's only 1% of 1% of my customers haven't been invoiced in the last 12 months at all. So what would I index here? Neville.
Last invoice date.
Last invoice date? Would you? He says in a Dorothy Dix voice.
Also, rewrite the query.
Okay, what's also rewrite the query? Thank you, Andrew. So why, using this query, why wouldn't I index last invoice date? Less than 1% of the rows sounds attractive. Because it's an expression, right? It's an arithmetic expression. Last invoice date plus 365. If I index last invoice date, it's not going to use that index because I've corrupted my expression by adding 365 to it. What could I do to it? Sorry? I could use a function-based index. Anything else? Andrew? Subtract 365 from sysdate. Yeah. So then I just have last invoice date left on its own on that side. So less than 1% of all rows. Probably useful to index that. Depending on the distribution on the table, you might actually find that a full table scan is quicker. Right? 1% doesn't sound like a lot, but it very much varies on the usage. You may find that the full table scan is faster, but it's the sort of thing you'd probably have to benchmark. But it's certainly a candidate for indexing if you rewrote the query. Neville.
Like saying it's mentioned +0 there, which will turn off the index if it happens to be one.
Sure. So that's working the other way around. If something's using an index and you don't want it to because it's slower to use the index, you can add an arithmetic expression or a concatenation expression or some sort of function to stop it from using index. Until someone comes along a few months later and goes, oh, look at that, I'll index that function. That'll make it faster. Righto. What about this one? What would we index here? Select same columns again, from customers, where last invoice date is greater than sysdate -7. So I want customers that have been invoiced in the last week, and all my customers are indexed monthly, so that's about a quarter of the rows in my 100,000 row table. What would I index now? Nothing. Why? Full table scan is probably going to be faster for a quarter of the table. 100,000 rows. I'm not going to go, it's 25,000 rows, a quarter of the table. I'm going to do 25,000 block reads. That'd be terrible. Okay. Sorry, was there a question? Rule of thumb there. I hate rules of thumb, and you know that, which is why I asked the question. The rule of thumb that I give is that if it's more than 10%, I'd be very, very surprised if an index scan that also looks up the table is faster. More than 10%, I reckon a full table scan is always going to be faster. Less than 1%, I don't think I've seen an example where less than 1% the full table scan is faster. I reckon an index is always going to be faster for less than 1%. The mid-range of 1% to 10%, that's the grey area. Okay, that's when you've got to start benchmarking. But so if you're looking for a rule, if you're going to read less than 1% of the table, you'd be pretty confident an index is going to be the right way to go about it. Righto. Done that one. Example 4, what would you index? Select customer num from customers where last invoice date equals trunk sys date minus 1. So customers that were invoiced yesterday, 5% of all rows. 5% is, it's in the grey area. Yeah? Index might be good, might not be good. What are we going to index? Sorry? Last invoice date, and maybe see how it goes. All right. Any other ideas? And customer number. Okay, if we put last invoice date and customer number in there, how does that help? I only have to go to the index, right? So that rule of thumb that I mentioned before, that 1% to 10%, that's for index scans that need to look up the table. Okay, because remember everyone saw the buffer cache doing all that work. Okay, those are the table lookups. Okay, if you don't have to look up the table, you don't have to do all those table lookups. Right, so the 1 to 10% rule. Everything, all bets are off if you don't need the table. So for this one, it might depend on how often you ran this query. If you're running this query once a day, you might not care. Okay, but if you're running it constantly, like if there were lots of executions of this, you might go, oh yeah, customer number. That's not too much to add to the last invoice date index. So yeah, if it's commonly used, it's going to be a big advantage to your solution. Yeah, sure. Add customer num to the index. Last one, I think. Save the good one till last. All right, we've got a join finally. Not all SQLs in our solution can be done without joins. All right. So into the tricky stuff. We're joining invoices and customers. We're joining it on the foreign key on the customer num. So the invoices table has a customer num, the customer table has a customer num. Customer num is a primary key in the customers table. We've got two conditions there. We're filtering on the customer where the name equals Presley, Elvis A, and there's exactly one row in the customers table for Presley, Elvis A. And the invoice date, just looking at invoices, not those invoices just for Elvis, but invoices for everybody, greater than or equal to add month sys date minus 12. So 12 months ago, customers invoiced, or invoices produced in the last 12 months, if you like, is 20% of all rows in the invoices table. Not all of which are going to have been sent to Elvis, of course. Very few of them, you might imagine, would be sent to Elvis. So what am I going to index here? Customer number. In which table? Both tables have customer number. In both?
No.
No? Which table? Sorry, invoices? Yep. Okay, so I've got customer number in the invoices table. Anything else?
Invoice date.
Invoice date in the invoices table. Why am I? So I've now got two indexes on the. Sorry, one index, two columns. Okay, cool. Yep. Customer name in the customer table. Okay, so what am I going to do? I'm going to go to the customer name index, look up Elvis, find the Elvis entry in the customers table. Okay, that gives me the customer number. Right, I'm going to use that customer number to look up the index on invoices, customer number, and invoice date. What am I going to? Is that customer number invoice date or invoice date customer number? Customer number first, invoice date second. Why? Right, first one needs to be in a quality condition. If you want to use the second one, first one needs to be in a quality condition. Okay, so our customer number is in a quality condition. That's the join condition. Okay, the invoice date is a range condition. Okay, so once I've used a range condition in a concatenated index, I can't go and scan on the next column in the index. So it was date and then customer number. I'd be able to scan on the date, but I'd go through 20% of the entire table because I wouldn't be scanning on the customer number. Right, so yes, that's exactly what we'd do. We'd index the customer name. Optionally, you could think about adding extra columns to that, but look, we're going to be selecting the customer name and customer address. We're going to have to look up the table. We're not going to add all those things to to the index. So we're just going to index the, we're going to pick up the address and the customer number. We're not going to add both of those into the index. So we've got an index on customer name. That'll help us find our customers row. Then we're going to join to the invoices table on the customer number, which could be dozens of invoices over the history, over Elvis's history with the organisation. But we're only going to get those invoices that are dated in the last 12 months. And because we've got invoice date in our index, we don't have to read all of his invoices going back years and years. We can go straight to the point in the index where 1 year ago, where those invoices, and maybe we've got monthly invoices, and we read through the 12 of those. Okay. Lastly, looking at our from clause, we said we're going to start with customers, but my from clause has invoices first and then customers. Is that a problem?
Not anymore. Those days it would have been.
What days are those? No, it's a common misconception. The order of tables doesn't matter as long as we're using indexes. That if you do go back far enough, Oracle used to use rules when it couldn't use an index. If it had a look, goes, oh, no, nothing there that I can index. It had the order of tables in the from clause used to be important when you couldn't use an index, right? But if you could use an index, the order of tables wasn't important, and it's still not important now. Not even when there's no indexes. So order the tables however you like in the from clause. All right. This was the first presentation in what might turn out to be a much longer series of Oracle-specific SQL tuning lectures. There's a lot of ground to cover in SQL tuning. The next one that I have planned is stepping up a bit on indexes, the index masterclass, talking about fragmentation, clustering factors, rebuilding indexes, avoiding index rebuilds, and that age-old question that everybody wants answered: why doesn't Oracle have clustered indexes like SQL Server? Everyone wants to know about that stuff. Yeah, just me again. Yeah. Okay, cool. All right, and that is it. Open to questions now. Has anyone been saving a doozy for me right to the end? Yes?
What's the default buffer size?
Default buffer size. That's set by your DBA when you create the database. With current versions of the database, there are several components of memory. The buffer cache is just one component of memory. There's other components of memory that Oracle use, and they are all dynamically sized now by default. So you can, when you're installing a database, you can give it a maximum, give Oracle a maximum to use that covers all of the possible uses of memory, and it will allocate memory for all usages up to that maximum, but not exceeding it. And then, if it needs more for the buffer cache and less for the large pool or something, then it will dynamically reallocate memory. As much as you give it is the answer to that.
Can you disable an index?
Can you disable an index? In version 12, you can. I think it's called hidden indexes in version 12. 11.2 I can't remember when hidden indexes were introduced. It was either 12 or 11.2. Prior to that, no, you can invalidate an index, which is not quite the same as disabling it. So it doesn't. If you invalidate an index, it won't get maintained anymore. When you insert and update the table, it won't get maintained. If you want to, if you've got an invalidated index, you want to validate it, you rebuild it from scratch. Okay. If you've got an invalidated unique index, then you can't insert anything into the table. So don't go willy-nilly invalidating indexes. Yes?
Slide availability?
Slide availability. I will. I'll be sending out a survey for which you're free to say that you enjoyed the presentation immensely. And at the end of that survey, after you've said that you enjoyed the presentation immensely, I will give you a link where you can download the slides. Also, within an amount of time that will be determined by Murray's availability and spare time, the video of the presentation will be up on YouTube. If everybody here is interested, I can send it out to the people that send the link out to the people that accepted, and you can rewatch and show it to your family. Michael, can you enforce the use? Yeah, can you enforce the use of a specific index? So people heard of hints in Oracle? Yeah, hints. The documentation says that that hints are only suggestions to the optimizer. That the optimizer is free to ignore hints. There are ways to write hints in such a way that they are not ignored. So if you tell it to use an index and you supply all of the other appropriate hints required, you can force it to use that index, providing, of course, that index exists and that the rest of the execution plan that you're specified in your hints is valid. It's also possible to essentially save an execution plan so you get a SQL just right, just the way you like it on a test system. You can essentially export the execution plan that's using that index and import the execution plan into production, and then or any other database you like. Maybe you export it from production where it's working just right and import it into your test system, and then as long as nothing else changes, like no one drops the index or does something else to the database, it will always use that same plan if you've imported it. So yes, you can enforce the use of an index. John?
Bit of a general question, but what do you think performs better, Oracle or SQL Server?
That was always going to happen. Look, Oracle and SQL Server, and this will surprise a lot of people that know me well. Oracle and SQL Server are both enterprise strength relational database systems. If you choose one over the other and your implementation fails, don't blame the database, blame yourself. Okay, they're both excellent relational database systems. For most applications, they are both they're both going to perform admirably and up to your required specifications. There are things that you could do to tip one or both over the edge. Certainly, big data type applications, you can scale things up to a level where both won't work, and it's not a matter of one will fail out before the other. It will very much depend on your application and how you've written it. I would, if I was coming into a greenfields project, I wouldn't especially care which database was chosen, regardless of the requirements for that project. I think both can certainly be made to deliver successfully. Does that answer your question? Kind of. Andrew?
What do you do with Ross?
For the video, the question was, who are you and what did you do with Ross? Andrew presumably expected me to say, Oracle, 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 what's this SQL Server rubbish? Yes?
Is it still worth using indexes with SSDs?
Is it still worth using indexes with solid-state drives? Absolutely yes. If you stick a table with 1 billion rows in it on a solid-state drive, it is, and you do a full table scan of that table, you're still going to be going back to that table a lot of times. It's actually it's a misconception, I believe, that the disk is the limiting factor. So when we talked before about those disk reads being the slow bit, okay, there's actually two things at play in there. In an enterprise system, our disks are almost always network disks. Okay, they're not disks. Our databases are very rarely disks that are mounted on that are physically present on our database server computer. Okay, they're SAN or NAS, or they're disk devices that are external to the computer. And most of the time spent in going and getting data is actually the network latency. Okay, going over to the disk, okay, going over and then coming back across the network is where a lot of the time is spent. Of course, yes, there is time in, especially with spindle disks, in picking up the data off there, but you cannot discount the network time. If you've got a network-mounted database and you decide, oh, let's go solid-state disks to really give our application a boost, don't be surprised if you don't get the results that you want. Yeah. Yeah, certainly the thing about indexes, the purpose of indexes is read fewer blocks. If you read fewer blocks, you're going to take less time. Any more questions? Judith?
I should have asked you at the beginning what was clearly irrelevant or relevant to SQL.
Okay, what's the relevance of this presentation to SQL Server? Indexes in SQL Server do use B trees. Okay, so the understanding that I've given you of the B tree data structure is completely relevant to SQL Server. What I described about the DB file multi-block read count, SQL Server has an equivalent of that. So when we read the table and we come back with multiple blocks, SQL Server does have an equivalent of that. Where it slightly falls down is SQL Server. Shut your ears, Andrew, don't listen to this. SQL Server is in one way a little bit cleverer than Oracle. There is one class of reads from an index that can do multi-block reads from the index when you're doing a range scan. Oracle can't do that. Oracle's one block at a time. So a lot of it is relevant to SQL Server, but not precisely relevant. Does that answer your question? Any more? All right, looks like we're about done. So we're nearly 7 o'clock, which is just right on time. Thank you, everyone, for giving up your evening to come and listen to me go on about indexes.